Hello. Next talk. My name is Jehan Tremback, and I'm going to present an idea I've been working on for almost 2 years called Althea. Working on it with a guy called Justin Kilpatrick, who couldn't be here today. Couldn't make it out to Austria. But anyway, Althea is, we call it incentivized mesh. And it's kind of a network structure and planned for a set of protocols and modifications to existing protocols to allow routers on a mesh network to pay each other for bandwidth. So there are, so the reason we're doing this is there are a lot of wireless ISPs in the US, in the Bay Area, definitely. And a lot of people get service through wireless ISPs, probably a lot more than get service through community mesh networks. So the idea of Althea is if we can automate a lot of the payments and allow people to set up equipment, mesh it with each other, and get compensation for their contributions to the network without being part of a company supplying an ISP, it will increase competition to ISPs and allow people to switch providers more easily, and hopefully result in lower price, higher quality service. So I participate in peoplesopen.net in Oakland, and it's kind of hard to find time to expand networks, and so by adding money to the protocols, we'd hope to make it possible to make a mesh network where people are getting compensated without it being like a business where customers are locked in. Also another thing I noticed with peoplesopen.net at least is that a lot of our nodes are connected only over VPN. So we use a similar network structure to Freifunk and WLAN Slovenia, where there's a VPN and the nodes are meshing over the VPN if they don't have a physical link. And it's just a lot easier for people to have nodes in their homes. But that's not really like a network that's supplying internet access because they're connected to an ISP at every node. So I've been doing outreach to people with like tall buildings and business owners and stuff. And a lot of these people are accustomed to charging rent for transmitters on their roofs because it's something they already do. They charge rent to cell phone companies, they charge rent to wireless ISPs, and we, as a nonprofit of volunteers, we don't have the kind of money to pay them the rent they're charging. So perhaps if users are paying a little bit, we can also pay the building owners without being a centrally administered ISP. And I want to be clear also, something that's running on peoplesopen.net. These are pretty much as ideas and plans right now. I don't know if it'll ever run on peoplesopen.net, but that's where I've gotten a lot of my experience with mesh networks. So, okay, so the structure is basically based around pay for forward. So routers pay each other for, in a lot of ISPs, the way they work now is you pay for upstream and downstream access to the internet. But with Althea, what we're planning is that routers actually, like sort of the base primitive is that routers pay each other to forward packets. Because routing protocols propagate metrics about forwarding packets, and you can choose who you want to send a packet to have it forwarded. You can't really choose who you're going to receive a packet from, so it makes a lot of sense. On top of that, we build a structure allowing people to pay for internet access in a more user-friendly way, obviously. The payments happen with cryptocurrency payment channels, and payment channels are a technique by which you can send another node a payment using only one packet. So with cryptocurrencies, you have to wait a long time, usually for confirmation, like several minutes. There can be a pretty hefty transaction fee, like $2 on Bitcoin. With payment channels, you get rid of that. You put some money down beforehand, and then nodes exchange signed messages to make the payments. And obviously, conventional payments with credit cards and stuff are faster than blockchain payments, but they also have some time to packets need to be sent to the bank and back and stuff, and also there are fees associated with that. So payment channels payments to me made very quickly and with very low overhead. So the prices are propagated by distance vector. So you're probably all familiar with how distance vector protocols work. They propagate metrics, and the metrics are additive, and higher is worse. So prices propagated the same way. The higher the price, the worse. And so each node sees their neighbors. They see the metric to a certain, for each destination for each neighbor, they see the metric to that destination and the price to that destination. And with that, they can make choices on which neighbor to send a packet to for a given destination and alter the routing table in the kernel. So, and then also the network architecture is based on the exit node model, where you have an exit node that's sort of connected to the internet, being connected to over tunnels, over gateways or uplinks who have internet connections. The exit node actually, though, does the natting and takes the heat for any legal issues resulting from the use of the connection instead of the person who's actually contributing the internet connection. So, and also the exit node in Althea does some other stuff having to do with changing the pay-for-forward model into paying for the entire path. So I've also got some diagrams now. So distance vector with additional price field. So basically, it looks like those letters X and N didn't show up that well, but it's saying, B is saying to A, I will forward packets to destination C at quality X for cost N. And then we also have some nodes in between them, however many, and then A is choosing whether to forward packets through B based on what B tells it, a distance vector protocol. And we're using, well, we're looking at using Babel. And then also nodes charge each other for forwarding. So B keeps track of how many kilobytes A has forwarded for A, and also the destinations they're forwarded to, and how many tokens it costs for each of those destinations at a time, and comes up with sort of a bill and tells A, you owe me this number of tokens. And then A can pay the tokens. If A doesn't pay the tokens, B can cut off A's connection and stop allowing it to, stop forwarding packets for A. Let me think if I'm forgetting anything. Yeah, and I'll get into how it cuts off A's connection a little later. Oh, and I want to say with the payment channels, this can happen very quickly. So B is trusting A a little bit to actually pay it, but it doesn't have to trust A a lot because the payments can happen very quickly with one packet, so it can be payment for, just for a few kilobytes or something. Although I don't know how much of an issue that really is, but that allows it to allow a very small amount of trust. So as I was saying, pay for forward, the user node, and that's what I call the nodes that have some clients connected to them, are providing internet access to people using the internet. The user nodes pay upstream. So if you want to get packets to the uplink and then to the exit node, you're paying your neighbor a larger amount, and your neighbor is paying their neighbor a little bit smaller. And these prices are what have been propagated by the distance vector routing protocol, so they all line up, and each node in the chain is making a small profit on that forwarding. And then the exit node pays downstream on behalf of the user node. So you'd have to have some arrangement between A, so C is the exit node there, some arrangement between A and C, and so A sends C a little bit of, sends C some money, some tokens, and so then C, once it receives the request from A, C then uses the tokens that A has sent it to send the packets back through the network to A. And so that way you preserve the pay-for-forward model, which is elegant in a lot of ways, while also providing response traffic. Because the way most people use the internet, the response traffic is actually a lot more than the request traffic. So another thing which I haven't covered yet is if you have a distance vector routing protocol like Babel, it's propagating routing metrics, and you have this financial incentive involved. Right now, I don't know of any distance vector protocol where this isn't a problem, but you're basically trusting your neighbors to be honest about the metrics, the quality metrics for other nodes. So I could tell you, if you're connected to me, I could tell you, oh, I have this great path to the destination you want to get to, but actually the path is not that great. I'm dropping the packets, whatever. And there's nothing stopping anyone from doing that right now in routing protocols. And that's also known as a black hole attack, but it could also be an attack where it's not a black hole, where it's actually just a reduction of service. So the service is not quite as good as was advertised. So what we're trying to figure out, we're working on modifications to Babel right now, is for nodes to be able to verify with destinations how good the route actually was. So in Babel, nodes send hello and I heard you packets back and forth to their neighbors, which gives them the link cost estimation, and then those are added up to give the route metric. And so we think that if we can send hello and I heard you packets from a given node to a given destination, then you can look at the cost you've estimated from that and then compare it to the cost that was advertised by a given neighbor, and then see if that neighbor is actually accurately reporting the metric. And this won't work, for example, it won't work with Batman 5 because Batman 5 uses a metric that's based on the like the rate of the physical Wi-Fi interface, and I don't think it's possible to sort of get an equivalent number over an entire route. So with Babel, it's pretty simple, and it's just based on packet loss of hello and I heard you packets, also an optional round trip metric. Both those metrics, I think, could be equivalent to the entire route if you go from a node to a destination. And I'll also, a little later, I'll get into how nodes, like once nodes have done this verification, how they use that information to establish the reliability of neighbors. So, okay, also, as I was saying, if A is not paying B, then B needs to stop forwarding A's packets, because the whole forwarding of the packets is based on this condition of payment. And you could do this by looking at A's MAC address and blocking the MAC address. That's vulnerable to spoofing, of course. Another way would be for A and B to use WPA to secure the connection and authenticate it. That's an option where we've actually chosen to use tunnels so that it will work on wired links and be a little bit more flexible in general. And also there's other things. Some interfaces don't allow you to have like a bunch of different SSIDs and stuff. If you want to have a different, WPA shared key with each neighbor, that might be a problem. So we're looking at using WireGuard tunnels to do the authentication between neighbors to allow and disallow forwarding. So this is a diagram of the tunnels that are involved. And so here we have user node, intermediary, or gateway nodes. And the user node has this per hop tunnel with its neighbor. And then each neighbor after that also has per hop tunnels. And the per hop tunnel is a WireGuard tunnel, and it can be shut off if the node is not paying. And here's a diagram. So you have a physical interface. You have WireGuard. WireGuard branches out into a bunch of virtual interfaces. Firewall can cut either one of those off, and they get bridged back together into user space. So then also, there's the exit node tunnel. And that's kind of an extra layer of security. So that's between the exit node and the user node. So I don't think that's present in a lot of mesh networks right now. But we need that because I was talking about these verifications. You don't want B, if B is trying to cheat you, you don't want B to be able to see the hello and I heard you packets. So by going through a tunnel, they're encrypted, and B doesn't know what they are. Have to have some sort of traffic to mask it as well. You probably want to make it so they're not some recognizable size for the hello packets and that kind of thing. And then also the exit node tunnel also makes it so that the neighbors around someone don't know they're browsing, don't know what they're doing on the internet. Obviously they should be using HTTPS, but there's still leakage of what sites they're browsing and stuff. So there's a little extra security. And WireGuard tunnels, according to, we haven't done really rigorous tests on this yet. We're still under a lot of development, but WireGuard, according to their benchmarks, is is very fast, and it shouldn't cause too much overhead. And then also the per packet size overhead is also not that much. So it should be a good way to do it. And then you can see here the exit node is doing that, and it's going to internet destinations, and data packets are going to the user. And so it's like basically the user has to choose an exit node that they're going to use. And the exit node has a relationship to them that's kind of like an ISP. The exit node is responsible for their use of the internet legally, and the exit node also can see their browsing history. And then the nodes in between, the intermediary nodes that are around the city or whatever, carrying the traffic, and also the nodes that have internet connections that are getting the packets to the exit nodes, they are not responsible for this, and they also can't see it. So it's kind of like you have this ISP relationship, and then you have a physical layer, which is sort of interchangeable and has like, I don't know, like risk-free, but it's like you don't have to worry about who you're connecting through, what they can see, and they don't have to worry about what you're doing. So that's the point of the tunnels, and we'll see how performant that is. So yeah, so I could probably go into more detail about each of these pieces, but I want to see if people have questions. Also, this is still, so like where this is in terms of being done is not that far along. Like we figured out this whole structure, and it took a while to think of how we make everything fit together with the pay for forward versus we were also looking at how you could use maybe pay for internet access instead of pay for forward, like more of a traditional model. But there's still like a lot of things we don't know for sure work. So, for instance, routing protocol verification might not work. So we still need to see whether we can accurately verify metrics based on going sort of end to end, and also whether it's possible, like there could be attacks, like you could tell that it's a verification packet as opposed to a data packet, so that might be an issue as well. Also, the network structure might be too rigid. I prescribed like it's a structure similar to many mesh networks today, but there are all these pieces that all need to be present, and that might be problematic if you need flexibility to be able to set up your network in different ways and stuff. But this system needs all these pieces. That might be an issue. And also, it might be too much overhead, mostly the tunnels, but other things as well. Maybe it's just not worth it. And then also social and business reasons. So maybe the payment of the node locations isn't that important. It's like more, I mean, to run a network, you need to administer it, make sure it's up, deal with it going down, deal with technical support. And so someone needs to do that. So we can come up with this technical system of this is how you can technically get these payments to each node who's participating, but then you also need some way for the people maintaining it to be able to, wake up at 3 in the morning and fix it and stuff. So that's another issue that could make the idea not be that good of an idea, really. How to guarantee uptime. And property is theft. That's more of joking, but I think that it could be that people who are interested in setting up networks for commercial reasons would prefer to have the lock-in that comes with being an ISP. So if I call up a wireless ISP and I'm like, hey, I want an internet connection, they'd see whether if they can reach me, they give me some hardware, and I then get on the internet with their hardware, with their network. If I want to switch to another wireless ISP, I have to call them up, get a new piece of hardware, they got to connect me and stuff. And so there's this lock-in, and Althea is meant to get rid of that lock-in to make it more efficient economically, but it might be that people who are really in the business of professionally setting up networks don't want to give up that lock-in. Now, on the other hand, people who are doing mesh networks, maybe most of you don't think it's a good idea to pay for internet at all, and don't want to set it up for that reason. So that's another issue. So I'll ask if anyone has any questions, and if not, I'll go into a little bit more detail technically on each of these pieces. So. No? Okay, so let me. All right, I'm not expecting you to read this, by the way. Just remind me of what I'm doing here. So, okay. All right, so this is the verification scheduling. And like I said, we have this technique for verifying routing metrics that have been advertised by neighbors. And the question is, like when do you do this verification over a given neighbor? And so at first I was looking at kind of stuff related to multi-arm bandit algorithms, and those are algorithms for doing clinical trials, stuff like that, where if you have a certain, like if you're trying a certain strategy that's more effective, you try it more often. And that's meant in clinical trials to make sure that the patients are getting the more effective treatment throughout the trial as opposed to less effective ones. And so I looked at using that, but we actually decided to just go with a straight up random sample. So you have kind of a round-based thing. Each round node chooses, like looks at the destinations that have been used in the last X seconds. I don't know, that would have to be adjusted as a constant. I'd also thought about sort of having destinations be selected more frequently based on how much they're being used. But I think that it's probably not that, like for a user, you might not actually be sending many bytes to a destination, but it might still be very important to your user experience to have good routes to that destination. So we just, for now, just randomly select one. That could be optimized. And then we look at feasible routes to that destination from the routing protocol, and then select one of those at random. And the route is a neighbor and a destination and the metric and stuff associated with that. And so then we test that. And so that consists of sending that the hello and I heard you between the destination over that specific neighbor, and seeing what comes back with some information about what neighbor that was going over. And then you get that back, and so basically this is, you're probably not going to like be able to follow this up on the small text on the projector, but we look at the destination that sent the I heard you, the neighbor shown by the I heard you message, the verified route cost shown by the I heard you message, and the advertised metric that the neighbor was advertising. And then update the accuracy score, which is it's the advertised metric over what was verified. So it's like a fraction of how accurate they were, and then update the accuracy like of everything the neighbor is advertising. And then from that, you get the sort of an average accuracy of that neighbor. And if that average accuracy is below some constant, then those routes are removed from the routing table and are not allowed on the routing table anymore. And this is not going to stop the neighbor from being tested. So the neighbor will still be tested. So if they improve their accuracy, they can get back onto the routing table. And this could be vulnerable to a Sybil attack by neighbors who are setting up a bunch of identities and with just one neighbor. So there needs to be, in this system, there needs to be some kind of outside Sybil prevention, like outside control. Like you have to join a community group and people know who you are and have your, or have some sort of it doesn't need to be really like a lot of vetting, but some kind of basic thing where you can't have somebody set up 1,000 fake neighbors. But yeah, and then that way, if each node is going to have like probably not that many neighbors, and so testing a neighbor that's been inaccurate in the past is not really a huge concern because you don't have that many neighbors anyway. Let's see what else we go over. So, oh yeah, and then also route metric adjustment. So once you've gotten the, you've got this overall sort of verified cost of the route, and you're seeing what your neighbor is advertising. But since you have this verified cost, even if you haven't kicked them off the routing table yet, you can still adjust the metric that you have for them. And then perhaps it's a little bit lower than what you thought it was before, and then so you select another neighbor for that route and put that in the routing table. So, and then that's, it's got this exponentially increasing timeout, so the more inaccurate they were, the longer that adjustment lasts for. So that's like a little optimization. And a little bit more about the price metric. In Babel, there's a sort of arbitrary external sources of willingness. That's where you can add a number to the metric that Babel is using for a given neighbor. And we don't want to use that for the price because this is the metric that's propagated and we're trying to verify this metric. So adding a number corresponding to the price wouldn't really work for that. And then also, we're propagating this price not only to select routes, but also so that nodes know how much to pay each other. So for those two reasons, we're working on a separate price field. So it's a separate number aside from the metric that gets propagated and gets added up through each node. And then that's used to determine how much to pay their neighbors. So let's see where it's, so we have a metric and the price field. The metric is M, and then it gets added, the price field gets added to the metric, and the price field is multiplied by a constant called N. And so that constant reflects how much you want to take price into account. So if N is lower, then it's going to be multiplied by the price, and it's going to reduce the impact of the price on the metric. And so you can choose, do you want to have cheap but low quality routes, or you want to have expensive high quality routes? So another thing we haven't really looked into that much yet, but it could be possible to populate multiple routing tables at different values of N and then propagate those metrics on different router IDs so that your neighbors could choose which of your router IDs that has different route selections they want to use. But we haven't really thought about how that would kind of work through the network. And I can tell you about the payments as well. This is probably the easiest part of the whole thing. It's payment channels which are being used in a lot of cryptocurrency things now. Basically what it is if me and you want to open a payment channel, we both deposit a certain amount of tokens. So I deposit 100 tokens, you deposit 100 tokens, and then when I want to pay you, so there's this funding transaction to deposit the tokens. And when I want to pay you, I send you a message with an adjustment. So let's say that my balance is 100, your balance is 100. I want to pay you 5 tokens. I set the adjustment so that your balance is 105 and my balance is 95. And I sign it and I send it to you. And now you have this message that can be submitted to the blockchain well, when you submit that, the blockchain adjusts the balances and gives and transfers the money back to the participants. So with this message, you can take it and submit it, and then you then get 105 out, and I get 95 out. And so once you have this message, like, you can consider the payment done because you have this thing that will let you get that out. And so if you want to actually get that out, you put your signature on it, well, give it to the blockchain and get your money out. So there's another thing. You could, of course, keep an old, so let's say I've paid you, your balance is 105, and then we have a bunch more of these transactions going back and forth, and your balance is actually supposed to be at 5, and my balance is at 195. But you take that old one from back in the beginning where your balance was at 105, and you submit that to the blockchain instead. So that would allow you to sort of get this money you're not supposed to have. So to prevent that, you put a hold period. And so the blockchain is not going to transfer the money back out for a certain amount of time. It could be a few hours or a day or a few weeks even. And so the transaction is then kind of on hold until that time is up. And so during that time, I could be checking the blockchain and seeing, have you tried to submit any old transactions? And if I see that you have, I simply submit the latest one. And there's a, I forgot to mention this, there's a sequence number on each one of these, sequence number on each one of these transactions. And so that way, if the blockchain gets a transaction that has a higher sequence number than the transaction that is in hold or on hold, it will honor the transaction with a higher sequence number. So that way I can stop, nodes can stop each other from fraudulently submitting old transactions. And so with that, it's like you can send a packet that just has a few hundred bytes, which makes a payment happen to your neighbors. And so that prevents neighbors from having to sell each other a lot of bandwidth on credit. So anyway, in terms of, I think I've covered most stuff here. So yeah, so exit nodes, again, to go over the exit nodes in mesh networks currently, they mostly are for legal reasons, especially in Germany. You're responsible for what people do with your internet connection. So if the traffic's going out over a tunnel and going to an exit node, you don't have to deal with that legal issue. Also, you can, in certain setups, you can have the deal with public IP addresses, do natting and stuff. They also provide the encrypted tunnel, so your neighbors can't see what you're doing. And then they're also the endpoint to verify routes. So if I'm a user node, I care about my the destination node that I use. You could have several on a network too, but I care about this destination node, and so I'm going to verify routes through my neighbors to that destination. And they're sort of the trusted entity on the other end who exchanges the hello and I heard you packets and tells me what the packet loss actually is. And then also going the other way, the exit node is of course being paid by me, the user node, to forward packets back to me. So it can also do verification through its neighbors of a randomly selected user node that it's servicing at any time. It's going to have to do a lot more verifications because it's sending to a lot more destinations. But you know, theoretically, exit nodes and also every node along the path, like the higher upstream they are, the more verifications they're going to have to tend to do because they care about more destinations. But the larger nodes that are higher upstream are going to have more capacity than your home Wi-Fi router or whatever. So so that should work out. And then they pay for return traffic. I went over that already. So so what I've laid out here is it's definitely in progress. We started writing a little bit of code and sort of working out the network structure and stuff and modifying Babel. But when all that technical stuff is done, we have to look at like what kind of network does this work well on. So it's kind of been designed with a mesh network or wireless ISP type of network in mind, where the user nodes are in people's homes and they're supplying internet access to their home Wi-Fi router. But it also might be possible to, this is not going to work on a client, like a dumb client, like a browser, just connecting to the hotspot, not going to work because it needs to do the tunneling, it needs to do the payments, and it needs to do the routing protocol verification. But it could be possible, certainly possible, to put it onto a small computer like a Raspberry Pi and make kind of a mobile hotspot. And that would then roam, even though it's Babel, which doesn't roam on layer 3. Since if it's running Babel, it will kind of roam, and it will be able to choose the lowest price and best quality connection anywhere. And then maybe it would be possible to put it on, I'm not sure, but to put it on client devices too. But they need to be able to run Babel. They need to have the different components. We need to have the privileges to be able to do what they need to do. You'd basically have to get access to the IP packets. But there is stuff on iPhone for proxies and stuff. So I think that iPhone, at least, and Android too, I think, have the access that's needed to run software at this level. But it would also be a huge amount of implementation work to make that happen. So where this is going forward is me and Justin are both working on it a lot. And we're going to try to sort of make a proof of concept, be a custom OpenWRT distribution, maybe it's too strong of a word, but sort of a custom setup, custom image, where we can demonstrate it working on a few Wi-Fi routers. And there's also obviously a ton of work around actually making it viable, making it work in the real world. So yeah. Oh, another thing, another possible problem with it actually is that if you really want to have high-speed internet access, it's really good to use directional antennas. And this whole thing is supposed to make it easy for you to switch between your neighbors they're getting access from and make it fast and easy to switch. But if you have to re-aim a directional antenna, that's not that fast and easy anymore. So if people wanted speeds comparable to like, you know, a good wired connection or fiber connection, that's theoretically possible with some equipment, but they would have to have a separate directional antenna pointing at each of their neighbors they're trying to get access from, who would also need to have separate antennas. But that's just a concern about directional antennas. And if you're using sector antennas or omnidirectional antennas, that's not as much of an issue. So I think I've pretty much covered it. There's probably not like 100% clear to you in every detail, and it's also not 100% worked out, but that's what we're working towards. And there'll be updates as we make more progress. So thank you.
Are there any questions? Nobody? Really? Ah.
So you're looking forward to really put this to work, and in what time frame are you planning to have a sort of running prototype? Sort of.
In the next year, I think setting up the tunnels and the architecture around that is not going to be that difficult. It's pretty. It's stuff that you already use in networks. It's nothing really that exotic. I could see also the payments not that difficult. It's just another matter of implementation challenges, just sort of doing the work. Modifying the routing protocol to work, that could have unexpected difficulties that could slow us down a lot if it doesn't work like we think it will. So, but barring any really unexpected things with the routing protocol modifications, I think that we should be able to do it in like a year. So maybe I'll present the results at the next BattleMesh. I don't know, hopefully.
Another question? Does not seem so. So thank you very much for your talk. And yeah, another word of applause. Next up dinner.
Yeah, next up dinner. So the plan is to move to Stiegelambulanz shortly before